Part 3 on black holes and gravitational forces, and I'm Claire Gilliam. Alright, so first we have our introduction. The purpose of this lab is to analyze the motion of an object undergoing gravitational force, and then use that to find the initial velocity of a spaceship in order for it to escape a black hole's gravitational force. Alright, so the tools we use are GoScript, which we use to create two models, one of a star orbiting a black hole and one of a spaceship launching off a planet orbiting around the same black hole. The physics principles we use were that Fnet, or dp/dt, is equal to perpendicular dp/dt plus parallel dp/dt. Then we also use the gravitational force equation and the position and velocity update formulas to simulate motion in our model. The results were we determined the mass of the black hole, we found the speed at which the spaceship must leave the planet to pass by the black hole or to orbit around the black hole, and then we determined that it's easier to find the change in momentum instead of calculating the net force. Next, we have to model the experiment. So our assumptions are that there are no forces acting on the star, and that the system is the star and the surroundings are the black hole. It's the same for Model 2, except we say that there are no forces or other forces acting on the spaceship or planet, and that the system is the spaceship and planet, and the surroundings are the black hole. For Model 1, we see that for the force of gravity on the star and the force of gravity on the black hole, they're going to be equal in magnitude but opposite in direction. For Model 2, it's similar. However, we have to take into account the gravity from the planet, the black hole, and the spaceship. Next, we have our computational models. So first, we establish g is equal to 6.7 times 10 to the negative 11th. The mass of the star is given as 2 times 10 to the 30th, and then we have to calculate delta t by multiplying by 24 times 60 times 60, as we're given that it's initially 1 day. All right, so next, our final conditions are that the momentum of the star is going to be equal to its velocity times mass. Then we use this to calculate the change in momentum and the change in velocity. We then plug this in for the change in momentum over change in time, which is also equal to the net force. We calculate p hat as the momentum over the magnitude of the momentum, and then plug this in to find the change in magnitude of momentum over change in time. We multiply this by p hat to get the change in parallel momentum over change in time, which is equal to the net force of parallel. Then we subtract dp/dt by dp/dt parallel to get the dp/dt, or the change in momentum over the change in time, perpendicular, which is also equal to the net force in the perpendicular. For Model 2, we have similar initial conditions. However, we already found the mass of the black hole in the previous model as 1.62 times 10 to the 34th, and we're given the mass of the star is 9 times 10 to the 28th, and the mass of the spaceship is 7 times 10 to the 10th. Our final conditions are we find the force of the black hole on the planet and the force of the ship on the planet, and add those together to get the net force on the planet as it orbits around the black hole. Then we do the same thing for the force of the black hole on the spaceship, and the force of the planet on the spaceship. We add those values together to get the net force on the ship. We then plug these into the velocity update and position update formulas to get the motion of the spaceship as it passes by the black hole, and the motion of the planet as it orbits around the black hole. Finally, we have our discussion and our conclusion. So, for Model 1, we initially find the mass of the black hole is rewritten as the gravitational force equation. When we run the model, we get many values for the mass of the black hole. So we must plug this in to a data set and then solve for the average of those values, which we ultimately get as 1.62 times 10 to the 34th kilograms. So that's the mass of our black hole. For Lab 2, we find that the velocity in the x direction for the spaceship to pass by the black hole without hitting either the planet or the black hole, it must be negative 5 times 10 to the 7th. In the y direction, the velocity must be 3 times 10 to the 6th. So, what are our possible errors? Well, for Model 1, we might not have had enough data points, which could lead to mass inaccuracies for the star. Next, for Model 2, our errors could have possibly been, because I had a guess and check, our initial velocity might not be as accurate. There might be an even more accurate value. All right, our concluding questions for Model 1. What does it mean? How are net force and parallel and rate of change of momentum different? Well, we see that net force is equal to the change in momentum over change in time. However, calculating the net force is much easier because we generally will know the mass of the object and the final velocity minus the initial velocity. This makes it much easier than having to calculate all of the forces and add them together. Our concluding question for Model 2, what if we wanted the spaceship to orbit around the black hole? Well, by using guess and check again, we see that the ship's x velocity must be negative 1.3 times 10 to the negative times 10 to the 6th, and in the y, the velocity must be 1.11 times 10 to the 7th. This would look like this. Here, in the magenta, we see the spaceship orbit around the black hole.